Okay, a non-empty set non-empty subset S of R is called a multiplicative system if there are two conditions. The first one is that 0 is not in S, the 0 element of the ring is not in the subset S, and the second condition is that S is closed under multiplication, implies S1 S2 also belongs to S. If we can find such a subset in a commutative ring with unit element, then that subset will be called a multiplicative system. Fine. Now what about this? Let M be, so this M that we are now going to write something about this set, it's going to be a set of ordered pairs. It's just like the M that we encountered while constructing the field F in our actual theorem. So we will go parallelly and then we see how far we can go. Let M be the set of all ordered pairs R comma S, where R is coming from the ring unrestricted, but S is coming from the multiplicative system S. Now just like our previous case, here on M we will define a relation which will turn out to be an equivalence relation. We will have to show that. In M, define a pair R comma S to be related to another pair R prime comma S prime if there exists an element, yes, an element S double prime in S such that S double prime times R S prime minus R prime S is equal to 0. Note that this relation is slightly different from what we considered in our proof of the actual theorem. There we required two such things to be, two such things will be related according to our previous relation if this is 0, this difference. However, now we require that there be an element in the multiplicative system such that not just this difference but the product is 0. Okay, so it is somewhat more general in some sense. Okay, so this is the setup. Now come the subdivisions, the parts of the question. A, prove that this defines an equivalence relation on M. Okay. B. Oh, but before B there is something else. So once we have proved that this is an equivalence relation, then there will be equivalence classes. For that we will devise some notation. Same notation, let the equivalence class of this ordered pair R comma S be denoted by R comma S, just like before. And in place of capital F we are now going to write a new notation, and let Rs be the set of all equivalence classes. In Rs, just like in F, we defined two operations, addition and multiplication. Here also we are going to define two operations. In Rs, define R1 comma S1 plus R2 comma S2 to be equal to, the definitions are same, R1 S2 plus R2 S1 comma S1 S2, and product R1 R2 comma S1 S2. Okay, then we state B. Prove that the addition and multiplication described above are well defined, and that Rs forms a ring under these operations. So previously we had a field F, but now at least Rs is a ring, not necessarily a field but a ring nonetheless. Now there are more parts to this exercise. Now here comes the difficult question. Can R be embedded in Rs? Because you see, if you recall the definition of an embedding, it was between two rings. We don't need field. In fact, while we embedded an integral domain into a field that we constructed, the integral domain itself was not a field, it was just a ring. So here also we started with one ring R, then with the help of a multiplicative system S, we constructed another ring. Now the question is, can R always be embedded in RS, just like our actual theorem? That is the question. That is one part of the question. Then there are more. Prove that the mapping phi from R into RS defined by phi of A equal to AS comma S is a homomorphism. So you see that here they are defining the mapping just like how we defined our mapping in the proof of theorem 361. They denoted this element in the text by this notation, but here however they are writing the actual thing, is a homomorphism. So without thinking of anything much, if we just go parallelly whatever we have done previously, we get at least a homomorphism of R into RS, but that question remains whether it's an isomorphism, and find the kernel of phi. Two more parts are there. It's a huge question. E. Something can be said in general about the kernel. Prove that this kernel has no element of S in it. So S does not intersect with the kernel at all. And finally the last part, F. Although the ring RS is not necessarily a field, I mean we will see that it's not necessarily a field, but we can say something about the invertibility of some of its elements, and this part is about that. Prove that every element of the form S1 comma S2, where S1 and S2 are in the multiplicative system S in RS, has an inverse in RS. Okay, so that is the entire exercise. It took some time to write it down fully. So let us now go to the solution. Okay, I have to rely on what I have written here because the calculations are fairly complicated. Okay, so first part A. in part A we were asked to prove that the relation that we defined here is an equivalence relation. So I start off like this. The relation can be easily seen to be reflexive and symmetric. Is it really that easy? I leave that to you. Okay, you try to show for yourself that the relation actually is reflexive and symmetric. Keep in mind that the relation now we have is somewhat different than what we previously had. Transitivity we will show. So for that, let R1 comma S1, R2 comma S2 and R3 comma S3 be three elements in M. Keep in mind that M is the set of such ordered pairs where the first coordinate is coming from the ring which is unrestricted. It can be any ring element, but the second coordinate is coming from the multiplicative system S. Okay. Oh, such that R1 comma S1 is related to R2 comma S2 and R2 comma S2 is related to R3 comma S3. Then according to the definition, then we have S times R1 S2 minus R2 S1 is equal to 0 and S prime times R2 S3 minus R3 S2 is equal to 0 for some S and S prime belonging to S. That is the definition of two ordered pairs being related according to our new relation in this exercise. Okay, now we have, okay, this part is complicated. It's better I write here. Okay, now we have this. I will just copy shamelessly from here. I don't want to go through the hassle of thinking of this thing and then writing the expression. So this is S prime S2 times R1 S3 minus R3 S1. This is equal to S prime S3 times S times R1 S2 minus R2 S1 plus SS1 times S prime times R2 S3 minus R3 S2. You verify that this is actually the case. Okay, if you apply the distributive laws and see everything, I mean, you can see here S prime S2 S3 In the first term we have S prime, S2, S3. Apart from that we have R1, so we have R1. In the second term we have minus S prime, S2, S1. So here you see S prime, S2, S1. Apart from that we have R3, so R3, and there is a minus. What about the middle terms? This is S prime, S1, S3, R2. Here S prime, S1, S3, R2, this is plus, this is minus, so they cancel out. So actually this is consistent, there is no mistake. But now this is 0 and this is also 0, so that means this is equal to 0. And keep in mind, because of the fact that capital S is a multiplicative system and these elements are coming from S prime, S2, so their product according to the second condition of a multiplicative system, this element is in S. Okay, in fact we can write that also. Since S prime, S2 belongs to S, we have R1, S1 related to R3, S3. So this tells us that the relation is transitive. The other things, that the relation is reflexive and symmetric, they are actually easier than this. You go through them and you will see why they are easy. So this is transitive and hence is an equivalence relation. So now we have an equivalence relation, so we can create the equivalence classes, all those things we have done. And then we come to part B, where we have to prove that addition and multiplication, the way we have defined, are actually well defined, and the collection of all equivalence classes RS is actually a ring under these operations. You may think that I will again go through all the axioms, but that will not be needed, fortunately for us. Okay, so let us first try to show that addition is well defined. This we will show. So let R1, S1, R1 prime, S1 prime, R2, S2, R2 prime, S2 prime be 4 elements in RS such that this is equal to R1 prime, S1 prime, and S2 prime. And after that, just like this one, we will have some conditions. Then here, however, instead of writing the condition in terms of difference, we will just simply write it like this. Then T1 R1 S1 prime is equal to T1 R1 prime S1 and T2 R2 S2 prime is equal to T2 R2 prime S2 for some T1 and T2 in the multiplicative system. Okay, then again a horrible calculation. Okay, then this one, oh man. Okay. T1, T2, it is very bad looking because it involves addition. R1 S2 plus R2 S1 times S1 prime S2 prime. So this becomes equal to T1 R1 S1 prime. Let us first write the things down and then we will see whether what we have written is correct or not. T2 S2 S2 prime plus T2 R2 S2 prime times T1 S1 okay. So let us now verify. In the first term we have T1 T2 S1 prime S2 prime, T1 T2 S1 prime S2 prime, and R1 S2 okay. So just like that, here also we have T1 T2 S1 prime S2 prime, but R2 S1. So it is okay. Now we are going to use this one. So in place of this one we will write this, but actually we are going to anyway, let us just write whatever is written. T1 R1 prime S1 S1 times T2, oh this one stays the same, S2 prime plus T2 R2, so the prime moves from this to this, from S to R. T1 S1 S1 prime, this also stays the same. Yes. Now this can be rewritten in this fashion. T1 T2, so T1 T2 we will take outside, and then R1 prime S2 prime S2 prime plus R2 prime S1 prime. Okay, the primes we have to take S1 prime, but then we are left with S1 S2 S1 S2. Okay. Now what does this equation tell us? This is equal to this. You look at this. This happens when there is an element in the multiplicative system S, and when these two are equal. So looking at this from that point of view, this tells us that I mean what I'm trying to say, this comma S1 S2 is equal to this comma S1 prime S2 prime. See, since, but we are going to write that extra condition also, since T1 T2 belongs to S, we have R1 S2 plus R2 S1 comma S1 S2 is equal to R1 prime S2 prime plus R2 prime S1 prime comma S1 prime S2 prime. Is it really what we are getting? You see, we will multiply, if these two are equal, then we will multiply R1 with S1 prime and S1 with R1 prime. So that's what we have done. We have multiplied this with this one. Oh, sorry, what am I saying? This with this one and this with this one. That is, we are multiplying this with this one, that gives me this, and this with this one. So yes, they are equal, and this is nothing but R1 comma S1 plus R2 comma S2, and this one is nothing but R1 prime comma S1 prime plus R2 prime comma S2 prime, and that tells us that addition is well defined. Okay, hence addition in RS is well defined. Now don't be afraid, we are not going to dig any deeper here. We will just mention, and there are good reasons for just mentioning that the rest is also similar and it can be done. Actually, I have done it. If you want, you can do it for yourself, or you can just take my words for it. Okay, so next we are going to write this. It's easier to verify that multiplication on RS is also well defined, and the reason for that is that the definition of multiplication is much easier than that of addition. So actually that will be much easy to show that the second operation is well defined. Further, it's a routine task to verify that RS is a ring. Now, what is the reason for making such a bold remark that it's a routine task to verify that RS is a ring? The reason is that, you see, although the definition of the relations, the one we had in theorem 361 and the one we now have in this exercise, although these two relations are different, but we have come beyond the relations, right? And the definitions of addition and multiplication are both same. There we had them in F, here we have them in RS. The structure of those definitions are same, and ultimately on those definitions the properties are depending, because we have already shown that the definitions give us the definitions are well defined in this case also. So in showing the other properties, in case of F, did we have to go down to the level of that equivalence relation for once? No, we actually did not have to do that. We just worked with the definitions of addition and multiplication and showed that they satisfied all the conditions for F to be a field. In a similar manner, we can show that RS is a ring, but keep in mind that F was a field and you need to just show that RS is a ring. This can be done just like what we have done here. So that's why we have made this remark. And to make it more solid, to emphasize that more, we write this extra thing. They are exactly like the ones encountered in the construction of the field of quotients of an integral domain. Okay, so they are exactly like the proof of theorem 361. Right. In fact, RS is not just a ring, but this is a commutative ring with